Hello everyone. So in this lecture video, we're going to be talking about how to treat numbers. So we're going to be talking about significant figures, operations involving significant figures, scientific notation or scientific exponents. Okay. So in this case, however, the first thing we're going to do is we're going to talk about two different concepts of accuracy and precision. So in chemistry, especially at this point in time, we're going to start doing measurements. All right. And the way that we can actually check how good our measurements is by actually measuring how accurate we are and how precise we are. So in order for us to measure accuracy, we actually do this math, which is the measured minus the actual value. And the actual value is always going to come from me, divided by the actual value times 100. In order to be considered accurate, you need to be plus or minus 5%, okay, or better, so or less on that one. So here's an example. So let's say there's this liquid in the container, and I pre-measured it at 50.0 mils. So this is the actual value. You then poured it to a different container, and you read the new level at this container, and you read that the level of the volume of this liquid is now 49.7 mils. So now you have to compare your measurement with the actual value for the volume. So you do a little bit of math. And the way that you do the percent error is you take your measurement minus the actual value divided by the actual value. So you use the actual value twice and you multiply it by 100. And it just so happens that in this case, the percent error is negative 0.6%. Okay. So again, since this is less than 5%, all right, you are within the range and this is an acceptable measurement. Okay. So this is a very, very important concept. Now, precision, on the other hand, measures how good your measurements are, if you take multiple measurements. If you take multiple measurements, how close are those measurements together? Okay, how close are they together? So let's assume again it's the same problem. You have a 50.0 mils in this container. And again, we have some measurements, and what we did is we did some measurements. So you measured 48.5 mils, you measured 49.0 mils, and obviously this 49.7 mils. What you take is you take your smallest value, which is 48.5 mils, and you subtract it from the largest value. This is called the range. Largest minus least. And so you take 49.7 minus 48.5, and the number is 1.2. Folks, this is not precise. In order for this to be acceptable, okay, if you look at all these measurements, all of these measurements are in the 10th place. In order for this to be precise, your range has to be less than or equal to the 10th place. So if this answer was 0.2, yes, this is precise. But since this is greater than the 10th place, this is in the ones place, this measurement is not precise. Right? So be very, very cognizant about these two mathematical formulas, and I will give them to you if you do need them, especially during laboratories. Which brings us to significant figure rules. So numbers are not created equally in chemistry. Okay, just because you have a number does not mean anything. Okay, so and significant figures come from uncertainty. So if, let's say for example, if I see a crowd of people and I ask someone, hey, how big is this crowd? And if someone tells me, yeah, it's around 1,000 people, that is an approximation, which means to say that they are very, very uncertain in this case. So that number that they gave me, 1,000 people, is highly uncertain. So which means to say it's highly erroneous or high in error. Now, if I ask someone else, let's say like an organizer of this event, and he or she says there are 822 people exactly, that, folks, is an exact measurement, and there's no uncertainty, there's no error in that number. Okay, so in terms of significant figure, we're just saying which of these measurements have the biggest error and which of these measurements have the least error. Okay, so few rules. All non-zero integers are significant. That means 1 through 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the problem is where zeros come into play. And I think that the best thing for us to do is actually go into different examples. Okay, so I'm going to go to the next thing right away. And we're going to have some examples, and we're going to have the rules up here so we can apply them. Okay, so first number. 5,645. How many significant figures are in this one? So for this one, we have to apply rule 1. There are 5, 6, 4, 5 are all non-zero numbers, so therefore in this case you have 4 significant figures. Okay. Now we're going to involve some zeros. 20,095. Okay, so this number, folk, so 2, obviously 2, 9, and 5 are significant. So I'm gonna X them up. And so the only time that there's ambiguity is about zeros. So now the question is, are these two zeros significant? And it just so happens that if we apply rule 1, 2, 9, and 5 is significant. But if we apply rule 2, the sandwich rule, we can see that these two zeros are between two non-zero numbers. So therefore, these two numbers are also significant. So therefore, all the numbers shown here is significant. So therefore, you have 5 significant figures. Here we go. These are called leading zeros. Any zero in front of any non-zero number, okay? These are placemakers, okay? All of the zeros for us are not significant. The leading zeros, again, are never ever significant. Even if there's a decimal bar, never ever significant. So in this case, you have 2 significant figures, okay? Here we go. 450, right? This is where a little bit of an ambiguity comes again into play. For our purposes, we are always going to consider trailing zeros significant or not significant, okay, dependent upon the presence of a decimal point. Since there is no decimal point, this zero is not significant, so therefore this only has 2 significant numbers, okay? However, if we write 450.0, there's a decimal point, these 2 zeros then become significant, so therefore this have 4 significant figures. So go through a bunch of exercises in the book and make sure that you can accurately answer how many significant figures there are in every single unit that's given to you, single set of numbers, okay? Here's another one. In this case, 23,400, 0.50. Folks, we have to apply all of these rules except for number 3, because number 3 is never. So 2, 3, 4, and 5 is obviously significant. These 2 zeros are obviously significant because they're between 5 and 4. This trailing zero is significant. Why? There's a decimal point. So in this case, all of these numbers, including the zeros, are significant. So you have 1, 2, 3, 4, 5, 6, 7. This has 7 significant digits or significant numbers. All right. So that was just looking at sets of numbers. Now we have to apply this rule of significant numbers when we actually do mathematical calculations. So when we add or subtract, folks, what we do is we actually use the measurement with the least. When we talk about least precision, we're talking about the least decimal places, okay? So here we go. 567.6 minus 23. The answer is 544.6. If we look at this one, this is subtraction. So we will look here. This is in the 10th place. This measurement is in the ones place. Which one has, in this case, is the least precise? This is the least precise because this is in the ones place. So our answer also has to be in the ones place. And that's why we round to 545. Now, why did this 4 become 5? Whenever we round, this is the ones place, so we need to round there. We always looked at the number to the right. If that number is 5 or greater, we round up. This is how we get 545. Okay. Next example. Again, this is an addition this time. Again, this is in the 1000th place. This is in the 10th place. Our answer has to be in the 10th place. And that is why it is rounded to 65.9. Again, same rules apply. As you can see, this is the 10th place. We look to the number to the right. It's 6, so therefore this number gets bumped up to 9, and that's how you get that number. Okay. Here we go. This number, subtraction, 100th place, 10th place. The answer has to be in the, again, 10th place. But let's look at the 10th place in this case. Okay, the 10th place, folks, is 9. But the number to the right is 6, which means we can round up the 9 to 10. Okay, if we round this up to 10, that means this turns into 0, and that 1 gets added to this number. Okay, but now this 9 now turns into 10 again, and then that 1 again gets added to the next number. And so this becomes a 9, 0, and that's actually how you get that number. All right, moving on. So this is the rules when you add or subtract. There's a different sets of rules when we multiply or divide. Okay, when we multiply and divide, we actually count significant figures. So we're multiplying these two numbers. You have 3 significant figures here. You have 4. Which one has the least? 3. So therefore your answer has to be in the 3, has to have 3 significant figures. Now you might say, oh well, Abner, there's a 0 there. Well, the reason why I can write the 0 there, folks, is it's a trailing 0. So this is not significant. So therefore the significant figures are only 4, 2, and 9 in this case. Okay. Here's a division: 564.5 divided by 5.3. 4 significant figures, 2 significant figures. So the second significant digit place, folks, is on the 0 here. Okay, so we look the number to the right again. So this becomes 1, 10. Okay, or this becomes 1, and then this gets dropped and becomes 0. Again, only 2 significant figures because this 0 is not significant. All right, which brings us to exponential notation, folks. So exponential notation is basically when you see like anything that has like exponents, right? Times 10. Times 10 to the 3, negative 5, so on and so forth. And again, the best case scenario, folks, is for us to do some examples. Take home, folks, is anything that's smaller than 1 is going to have a negative exponent. Anything that's bigger than 1 is going to have a positive exponent. A few examples. If we convert this into scientific notations, okay, what happens, folks, is you just count decimal places. So the decimal place obviously is here. So you're going to move it 1, 2, 3, 4. So, and then there's 3 significant figures in this, so we need to have 3 significant figures as well. So that's why it's 4.56 times 10 to the 4. All right, so again, you count how many times you actually move it, and the rule here is, folks, is you can only have one non-zero number to the left of the decimal point. So you cannot stop here, you have to keep going. All right, here this is going to be negative exponent. So again, here's the decimal point. We're going to move it until we have one non-zero number to the left. Go 1, 2, 3, 4. 3 significant figures here. So therefore your scientific notation also has to have 3 significant figures. 5.64 times 10 to the negative 4. Bigger than 1. So therefore this is going to have a positive exponent. Here's the decimal point. 1, 2, 3, 4, 5, 6. Here's the 6. There's 4 significant figures, 4 significant figures as well. Okay. And here we go, folks. We're going to go to the right. So therefore this is smaller than 1. And if you count, you can see that this decimal place will be moved 8 times. That's why it's to the negative 8. Why do we need to write 1.0? There's 2 significant figures here. This one is significant and this trailing 0 is significant. All of these leading zeros are not significant. Okay, now what happens when I give you a scientific notation? You go to decimal form. It's just the reverse. And all this is negative 3. You move the decimal point to the left. See? So if you look at this one, you used to be here and you go 1, 2, 3, and all the gaps, all the empty spaces you fill with a 0. Okay? Negative exponent smaller than 1. Positive exponent bigger than 1. Here's the decimal point. 1, 2, spaces again filled by 0. Okay, negative 4, smaller than 1, again smaller than 1, 1, 2, 3, 4. Again, you can see here, this is again expressed, 2 significant figures, 2 significant figures. And last but not least, this here, which is to the positive 3, which means this is going to be bigger than 1. And you just move the decimal point 1, 2, 3, and that's how the gap again is going to be filled by a 0. All right. So hopefully this helps you deciding into, this is actually the most difficult topic that most chemistry students encounter. You will encounter a lot of problems doing this type of math. Please do some practice.